My name is Katie Breivik. I'm a graduate student here in Physics and Astronomy at Northwestern. I'm also a member of the Center for Interdisciplinary Exploration and Research in Astrophysics, or Sierra. And I'm going to tell you today about the stellar graveyard and how we are using the stellar graveyard to understand how stars are born, live, and subsequently die. I was born in Utah, so I like to say that I was born into astronomy, and I really had no choice in the matter of becoming an astrophysicist. Most of my childhood vacations happened at places like this, Bryce Canyon National Park. And when my family and I camped under the stars outside, this is what we saw. It's no wonder that I was enamored by the stars because they were so incredibly bright as I stared at them that it felt like they were staring back at me. Now, humans have been staring at the stars for thousands of years, and we've even been pointing telescopes at them for hundreds of years. So you would think that we had a pretty good handle on how they live and die, right? It turns out that the story's not quite that easy. It's very difficult to observe stars, and that's for one reason. It's the fact that stars evolve so slowly. As an illustration of this, I'm going to show you a movie of a nebula called Eta Carina. Eta Carina is a nebula that is caused by the explosion of a star in our Milky Way. Now, the data that I'm showing you here was taken between 1995 and 2008. Over the course of this time, the gas has expanded in a noticeable way. Now, you might think that I'm just playing with you and using Photoshop to make the gas look bigger. But if you look closely in the upper left-hand corner, you can see two stars that remain perfectly fixed. So indeed, this is gas expanding over the course of 13 years. Now, back on Earth in 1995, I had just started kindergarten, and by the time 2008 rolled around, I had already graduated high school. So a lot of things happened in those 13 years, at least according to me. One of which was that I learned how to stare at the camera when somebody was taking my picture instead of creepily looking out of the frame. So, as you can see, a lot happens in 13 years on human timescales, but really when we think about the stars, it's basically just a sneeze. So the stars are really difficult to observe because they evolve, like I say, for millions or billions of years. So astronomers have to get clever about how we study them. One of the ways that we do this is the same way that we study humans here on Earth. We take a snapshot or a census of the stars and we try to connect the dots. We look at the young stars and we look at the old stars and we try to figure out how to make the connections between the two. In the same way that if you were to gather a bunch of people, say at a sporting event, and take a picture, you could say, I know that young people like cotton candy, and I know that old people like beer. We're trying to do this same thing with the stars today. But this really is missing a fairly large portion of the picture, and the same goes for the way that we study humans. If you want to understand what the humans are like today, it's very important to look at the humans and civilizations of the past. And in this way, we study what I like to call a cultural graveyard to understand what the humans were like back when they were building these types of monuments. In the same way that we study cultural graveyards to understand humans of the past, we can study the stellar graveyard made up of dead stars, like black holes, to try to say something about how stars live and die and subsequently fill this stellar graveyard. Now, by the fact that the stellar graveyard is made up of dead stars, this makes it very difficult to observe. Black holes, by definition, do not emit light. So that poses a fairly large problem as an astronomer that points telescopes to collect light. However, there's something that we have on our side with things like black holes and dead stars. And that thing is gravity. These types of stars are so incredibly dense that they deform even space itself, as you can see here. This is a simulation of two black holes, one orbiting the other, and if you look closely, you can see a deformation of space. You can also see with the smaller black hole that's orbiting that it even has a tiny deformation itself. And this deformation of space is related to how much gravity these objects have. Now, you can think of this picture as sort of bowling balls laying on a trampoline, where the trampoline acts as the space that you and I live in. So if you imagine rolling bowling balls across a trampoline, you might think the trampoline must react in some way, right? And it does. And in the same way that if you drag bowling balls across a trampoline, when you drag black holes through space, they cause ripples in space. We call these ripples gravitational waves as gravitational wave astrophysicists. Of course, we name them after ourselves.
And these ripples physically stretch and shrink the space between you and me. And it's caused, as I said, because of black holes that are orbiting each other one around the other. So these gravitational waves are key to getting to the stellar graveyard. And I like to think of myself as a stellar archaeologist, but instead of being like Indiana Jones and having a whip and a cool hat, my tools are having a computer, and I don't use telescopes. I have a computer that I use to simulate the sources of the stellar graveyard like black holes, and my experimentalist friends have built detectors that look like this. Now you might notice that this detector, the Laser Interferometer Gravitational Wave Observatory, does not look like a telescope. In fact, it's pretty much just a ruler, but it's a really, really precise ruler. And this observatory measures stretching and shrinking of space from one end of the arm to the other. As a gravitational wave passes through, it makes our detector do the gravitational wave dance, which is this. It stretches and it shrinks in measurable ways, and by reconstructing how it stretches and shrank, we can tell you exactly what caused the gravitational wave that passed through there. Now, had this talk happened any more than a year ago today, I would have had to tell you that we hope to observe these types of things. But in fact, today happens to be the 1-year anniversary of the first gravitational wave detection that humans made. So you also might be wondering why I called this Whispers from the Stellar Graveyard. It wasn't really just a trick. It was for good reason. And it'll make a lot more sense when I show you this video of our data. Did you hear it? That was the first gravitational wave we ever detected. And I raised the frequency just so that you could hear it even better. So I maybe shouldn't have called this Whispers from the Stellar Graveyard. I probably should have called it Whistles from the Stellar Graveyard. But that is in fact what two black holes sound like when they run into each other. And in case you missed the first one, the cosmos gave us a kind of late Christmas present a couple of months later that sounded like this. And I'm going to raise it one more time because it sounds better. So it's clear that everybody loves the sound of these gravitational waves, and you guys are in luck. Over the next few years, we expect to detect hundreds of gravitational waves just like this from objects that make up the stellar graveyard. And by detecting these objects and filling out what the stellar graveyard is made up of, we can start to tell more accurate stories of how these stars are indeed being born, live, and subsequently die. Thanks.